Hi and welcome to Broadcom Training EN141. In this training and video, we will go over the concepts of Remote Direct Memory Access, that is RDMA, and then look at Broadcom Ethernet NICs, RDMA over Ethernet, that is RoCE solution. This is the list of topics that we will cover in this video. We will start by presenting the high-level overview of RDMA. This will be followed by some details on Broadcom NICs RoCE solution. We will then cover Broadcom RoCE congestion control algorithm, which is essential for real-world deployments of RoCE. Let's start with a high-level overview of RDMA. Remote Direct Memory Access, that is RDMA, allows an application on one host CPU to read and write data directly from a remote CPU's memory. The exchanged data is transferred directly via the NIC hardware across the computer hosts. The data exchange bypasses the operating system kernel and involves zero copy of the data. RDMA therefore enables high bandwidth, low latency, and low overhead communication to applications across two different hosts. Let us now take a look as to why RDMA provides high performance. The conventional way to transfer data across host memories is to use the TCP/IP stack. The TCP/IP stack resides in the operating system kernel and is implemented in software. Any data exchanged by the application using the TCP/IP stack involves copying of the data from the application memory in user space to the kernel space on the sending host and then copying of the data from the kernel space to the user space on the receiving host. The data copy is performed by the CPU and is very expensive. Besides the data copy, the TCP/IP stack is executing on the CPU as well. In contrast, RDMA offloads bulk of the transfer operation to the NIC hardware. Once the RDMA transfer is set up, the NIC hardware on the sending host fetches the data from the application memory in user space via DMA, then maps the data to packets and then transfers the packets to the remote host over the network. On the receiving host, the NIC hardware receives the packets, extracts the data from the packets, and then transfers the data directly to the application memory in user space via DMA. The NIC hardware also provides a reliable service by handling packet retransmissions for lost packets. Let us now introduce a few RDMA basics and describe at a high level how an RDMA transfer takes place. RDMA requires a set of queues for operation. These queues are a send queue SQ, a receive queue RQ, and a completion queue CQ. The send queue and the receive queue together are called a queue pair or QP. QPs are used to send and receive data to and from the remote host. The completion queue can be used to signal the completion of a transfer. Applications on each end of an RDMA transfer allocate QPs and CQs. Additionally, before an RDMA transfer takes place, the application memory in user space involved in the transfer must be registered with the operating system kernel. This process is called memory registration or MR and pins the application memory so that it is not swapped out of main memory. The QP information and the memory registration information must also be exchanged between the applications involved in the transfer. This exchange can be done either using an out-of-band communication, example TCP/UDP sockets, or using an in-band connection management protocol. Once the QPs and the MRs are set up and information related to them exchanged, an application can signal an RDMA transfer to start. This can be accomplished, for example, by adding an entry to a send queue requesting a read or write from the remote application's memory. Adding an entry to a send queue or a receive queue is also known as submitting or posting a work request. At this point, the NIC hardware fetches data from its host memory via DMA over PCIe, creates packets from this data, and then transfers the packets to the remote host over the network. The NIC hardware on the remote host receives the packets, retrieves the data from the packets, and DMAs the data into host memory over PCIe. The NIC hardware also performs any packet retransmission required for the data transfer. Once the RDMA transfer completes, the NIC hardware updates the completion queue to signal the completion of the data transfer. Let us now take a look at different RDMA protocol layers. At the top, there are applications that make use of the RDMA stack below them. RDMA is highly suited for applications that move massive amount of data across CPUs on different hosts. Examples of these applications are artificial intelligence and machine learning applications, such as image recognition and product recommendations. Storage apps such as VMware vSAN are also suited for RDMA. RDMA applications make use of the verbs layer below them. Verbs is an abstract description of the functionality provided to an RDMA application. The Verbs API provides an interface for operations such as creation and modification of queue pairs and completion queues, memory registration, submitting work requests, handling work request completions, handling asynchronous errors and events, and many more. Below the RDMA verbs layer are the RDMA transport and network layers. These layers are implemented inside the NIC hardware. The transport layer provides reliable delivery of data across applications, including packet retransmission for lost packets. The network layer provides network services such as packet creation, addressing, and routing. RDMA queue pairs can be of different type, such as a reliable connected RC or unreliable datagram UD. An RCQP is connected to only one other RCQP, which provides a reliable connection across both ends of the connection. An RCQP guarantees error-free and in-order delivery of data through the use of acknowledgements. A UDQP can be used to send single packet messages to any other UDQP. Below the network layer are the RDMA link and physical layers. These layers are also implemented inside the NIC hardware. These layers handle packet level transmission and reception, provide link level addressing, flow control, and error detection. The physical layer also handles physical medium specific transmission and reception functionality. The RDMA concepts covered so far are independent of the underlying network fabric. As can be seen in the slide, RDMA works over an InfiniBand fabric as well as an Ethernet fabric. From an application programming point of view, the underlying fabric makes no difference to how the application uses RDMA via the verbs interface. Verbs can even be used for IVARP, which is RDMA over TCP/IP. RDMA was originally defined to run over an InfiniBand fabric. InfiniBand provides a lossless transport but is not compatible with Ethernet as it requires an independent network of switches and host bus adapters. RDMA over Converged Ethernet, that is RoCE, brings the advantages of RDMA to the ubiquitous Ethernet networks. Ethernet networks are widely deployed worldwide, and RoCE uses the same NIC and switches as used for Ethernet. RoCE v2 packets are encapsulated inside a UDP packet and are therefore routable over an IP network. Broadcom Ethernet NICs implement the RoCE solution. As Ethernet-based networks can drop packets, RoCE requires its own congestion control algorithm. In contrast to RDMA, the traditional way to exchange data across hosts is via the Sockets API. Sockets API is available in the user space, but most of the underlying implementation, including the TCP/IP stack, is in the operating system kernel in software. Use of sockets for data transfers consumes the CPU and therefore slow as compared to RDMA. Let us now take a look at Broadcom NICs RoCE framework. Broadcom's Thor and Whitney Plus family of NICs support RoCE. This is a high-level view of the Linux RDMA core software. Most of the Linux variants have native RDMA support. The Linux software stack consists of RDMA-related user space libraries that are collectively known as RDMA core. Most importantly, RDMA core contains the libIB verbs library that provides the verbs interface to the RDMA applications. RDMA core is part of the Linux RDMA project on GitHub. The Linux software stack also consists of RDMA related kernel modules that provide the kernel part of the RDMA functionality. Below that, there is the firmware running on the NIC that programs the NIC hardware for RDMA operations. Broadcom provides a user space library, libbnxtre, and a kernel module, bnxtre for RoCE. These are required to use RoCE with Broadcom NICs. The Broadcom software components, that is, the user space library libbnxtre and the kernel space driver bnxtre, provide RoCE control path and RoCE data path operations via the NIC firmware and the NIC hardware. Besides Linux, Broadcom RoCE is also supported on Windows and VMware ESX. This is how Broadcom RoCE software and hardware components fit into the Linux RDMA stack. The RoCE user space library and the RoCE kernel space driver communicate with the NIC firmware and the NIC hardware over PCIe for both control path and data path operations. The RoCE data path is completely implemented in the NIC hardware. High performance computing HPC uses RDMA extensively, where data is exchanged via RDMA across multiple hosts and multiple cores in a cluster. Many HPC applications make use of the message passing interface MPI, which is a specification for parallel computing architectures, allowing data exchange between various nodes in a cluster. There are many implementations of MPI such as OpenMPI, MPI Chameleon, MWAPIC2 and Intel MPI, etc. MPI implementations can make use of Unified Communications X framework, referred to as UCX, which is a library for optimizing and achieving low-level software overheads in a communication path. Broadcom's NIC and RoCE software stack can be used for HPC applications that utilize MPI and UCX libraries on Ethernet-based clusters. Broadcom NICs support the PeerMem Direct feature. PeerMem Direct allows RDMA across peer devices. In this context, a peer device can be a GPU or other custom accelerator used for machine learning and artificial intelligence type of applications. PeerMem Direct allows RDMA across two peer device memories, where the two devices can be on two different hosts on the network. For PeerMem based applications, if the RDMA happens across host memories only, the CPU still has to transfer the data from the host memory to the local peer device memory. PeerMem Direct allows two remote devices to directly RDMA across each other's memory via Broadcom NIC. This transfer of data from the NIC to the peer device memory and vice versa happens over the PCIe bus using PCIe peer-to-peer transfers. For PeerMem Direct, an additional kernel module known as IB-PeerMem is required. This module is provided by Broadcom. The IB-PeerMem module communicates with the peer device driver such as a GPU driver that is provided by the device vendor. The PeerMem Direct feature can be exercised via NVIDIA's Nickel, AMD's RICL, and Meta's ParamBench and DLRM libraries and many more. There are two approaches available for PeerMem Direct. First is a proprietary approach via the use of IB-PeerMem module. The other is the DMA buff mechanism of buffer sharing and synchronization, which is proposed by the open source community. Let us now take a look at RoCE congestion control. Why is it required and how it is implemented in Broadcom NICs? Ethernet networks are lossy, meaning they can drop packets. Congestion in any network element, be it a network switch or a NIC, can lead to packet loss. Broadcom NICs implement RoCE congestion control algorithm known as DCQCN. DCQCN stands for Data Center Quantized Congestion Notification. DCQCN algorithm slows an RDMA flow when congestion is detected for the flow. Besides DCQCN, 802.1 QBB Priority Flow Controller PFC can be used to pause RoCE traffic when congestion is detected. PFC stops traffic for a time once congestion is detected. Ethernet switches in a RoCE network must be configured for DCQCN and/or PFC. Congestion control algorithms are necessary in a network to ensure maximum throughput and low latency. Congestion is inevitable in a network when the amount of traffic directed at a link or an endpoint is more than the link capacity. Network switches have buffering capability to handle traffic overload, but the buffers can be easily overrun under sustained overload, or buffering may add latency to data traffic. A good congestion control algorithm ensures that the network bandwidth is fully utilized with minimum overhead and latency is kept to a minimum. RoCE is congestion sensitive, therefore a good congestion control algorithm is necessary for RoCE. Broadcom NICs implement the DCQCN congestion control algorithm that is based on two things. The first is explicit congestion notification or ECN marking in the IP header of a RoCE v2 packet. The second is congestion notification packets or CNP transmitted by the receiver NIC to the sender NIC. As shown in the figure in the slide, when a switch in the network accumulates excess traffic, its packet buffer queue rises. When the queue exceeds a configured threshold, the switch marks congestion encountered or CE value in the ECN field of the IP header of the RoCE v2 packet. When the ECN marked packet reaches the destination NIC sends a CNP packet to the sender NIC. Upon receiving the CNP packet, the sender NIC adjusts its transmission rate to alleviate congestion. It should be noted that CNPs are generated per flow, which in RDMA parlance means per queue pair or QP. The CNPs carry the QP number to identify the QP that generated the RoCE packet that was ECN marked by the switch. Broadcom NICs implement CNP generation, CNP handling, and the transmission rate adjustment based on the incoming CNP rate in hardware. This means there is no software or CPU overhead for congestion handling. Please refer to the public docs shown in the slide for further information on Broadcom RoCE solution. The doc, Using RoCE with Broadcom NICs, has details on installing and using RoCE with Broadcom NICs including congestion control settings. The Introduction to Broadcom RoCE Congestion Control white paper covers Broadcom's congestion control solution in detail. The public presentations shown in the slide cover Broadcom's RoCE congestion control solution along with the use of Broadcom NICs for large-scale, high-performance compute, artificial intelligence, and machine learning applications.